Darcy lecture of 2021 and 22. Chen, he is professor of Earth and Atmospheric Sciences at the Indiana University, and he's also sabbatical guest with us until the end of October. So if you would like to meet him, we have the upper row afterwards, but also during this time, you still can make an appointment. It's a great pleasure for me to introduce you. And I want to say to the people who are joining online, please don't write into the chat because we cannot really follow this during the lecture. Please ask the questions in the end. So Chen will talk about hydrogeochemistry in the 21st century, and we're very happy to have you here. Please, the floor is yours.
Thank you. Do you want to dim the lights a little bit? Thank you, Mario, for the introduction, and I also want to take this opportunity to thank my Eawag colleagues for hosting me my sabbatical here. I've been enjoying myself. The Darcy lecture series honors French engineer Henry Darcy, who discovered Darcy's law that the gas and fluid flow in plasma media. 2 years before Darcy's death, Darcy performed this famous experiments. Those are the original sketches here. And at that time, he had a poor health. He resigned from his position in Paris and returned to his hometown, Dijon. And he did about 200 this kind of experiments. This is part of the original data. And he published the Darcy's law in Appendix D of the report called the Public Fountains of City Dijon, and the rest is history. But here today, we're not only celebrate Henry Darcy, the brilliant scientist and engineer, we also celebrate Darcy, the man who used his knowledge and skill to serve the society. At a very young age, he designed a water distribution system for his hometown Dijon. It's a masterpiece of hydro work. The city offered him a bonus, he declined. The city erected a statue and also named a plaza after him. And Darcy went on and earned the highest honor in France, the Legion of Honors. He was a well-respected man, humble and diplomatic. So today we face a lot of today's world we face water resource issues. We have more than 2 billion people who do not have access to safe drinking water. So we need to train the next generation of hydrogeologists and hydrologist students that they need to have not only Darcy's knowledge and skills, but also his devotion to the public good. Now, the Darcy lecture series was established in 1986 by NGWA. NGWA stands for the U.S. National Groundwater Association, and the Groundwater Foundation is a nonprofit arm of the organization. And first Darcy lecture was John Cherry, and he just visited here, Eawag, early this month. And my term started in the pandemic, so they extended another year. The Groundwater Foundation received more than 100 requests from 20 different countries. By May of this year, I gave 25 in-person lectures and 35 virtual lectures. And the virtual format helps to get to the wide audience. By May, the record shows about 4,000 people, 4,000 devices logging in. My student made these maps, and I'm very glad that the lecture reached Africa and South America and Southeast Asia. Now, I offer 3 different topics. The first one is how geochemical reaction aquifers connect to the climate change mitigation. I'm going to talk about this today, and also offer a topic on watershed scale hydrological model as a community site platform for research, teaching, and service. I talked a little bit in Mario's group and also in the WT group talk. Some of the lecture are recorded, and you can find the recording at the Groundwater Foundation or at my website. Okay, so our talk today, the topic of today is hydrogeochemistry. So let's first find out what is hydrogeochemistry, what does it do? So in this cartoon of a hydrological cycle, mainly show that at every step and segment of the hydrological cycle, you see chemical and isotopic processes. Particularly, I want to point out is the water-rock interaction, right? As water flows through rocks, it react with the minerals, and the reactions mostly occur at the mineral-water interfaces. And this is a part of hydrogeochemistry I'm most familiar with. But in short, at every step and the segment of the hydrologic cycle, you see chemical and isotopic processes. So its common definition of hydrogeochemistry is that it characterizes chemical isotope composition of natural waters, but actually we also study the mechanism and reason of this process. Because we want to interpret the observation data quantitatively, we also want to predict the future events. Hydrogeochemistry is useful to study water quantity and water quality. To study water quality, we use the isotopes and chemicals in water as traces to quantify water flow from one domain to another. To study water quality, we want to see what are chemicals in the water, what are their concentrations and their chemical forms. We also want to know the source of fate of the chemicals. Isotopes are typically very useful for forensic groundwater investigations. We also want to know the chemical reactions that can remove the contaminants from water, so providing a knowledge base for remediation. Now, hydrogeochemistry is a very small branch compared to the physical hydrogeology. It's reveals by looking at some of the publication statistics. So I look at the Web of Science, so basically the publication in the first 20 years of this century, so the cutting off line date is August 25th last year. I look at the major hydrogeology publications. So water resource research, groundwater, general hydrology, hydrogeology journal, and I use the topic geochemistry. The first number here are the articles with the geochemistry as a topic, and the second number is total numbers published in those journals, and you can see the numbers are quite small. I also looked into see the major geochemistry journals, environmental science, technology, geochemical, and applied geochemistry and chemical geology, and you can see more papers are published on groundwater geochemistry in those papers. So we see a little separation here. We are still struggling to integrate the flow part of research and the chemical reaction part of the hydrosystems. Here I put a quote in water resource research in 1990. But what the authors said here then is still true, that the geochemists focus on the fundamental process of reaction between water and mineral surface, and the physical hydrogeologists focus on the flow. And we really need to cross-train our students they should know both. The reaction occur in a flowing water system. And part of the objective of my talk is I want to encourage cross-discipline research. Now, the next part of my talk, I want to review the major advances in the last 20 years. And of course, this is a very broad topic. Hydrogeochemistry is a very broad topic. My review must be very biased and with that are heavily toward the water, mineral gas interactions, and I don't know much about organic geochemistry. So, that's my bias. With this caveat, we see arsenic contamination in groundwater has attracted most of the research. We see successful use of isotope traces to quantify water fluxes. We see significant advances in geochemical kinetics and also adsorption to mineral surfaces in series, in data, in modeling, and the geochemical modeling was transformed from an expert-only tool to almost everybody's tool. So the most researched and published subject in hydrogeochemistry is arsenic contamination. The scale of the effort to match the scale of the problem. So by one figure, up to 220 million people are drinking water that are affected by arsenic contamination. You probably know very well this is a map about arsenic contamination in Bangladesh. This is one of the worst humanitarian crises. Arsenic contamination does not only occur in developing countries. In some developed countries, we also have this arsenic problem. So this is a map of state Indiana in the United States where I live and work. About 11% of sampled wells have arsenic concentration greater than the water standards. This is from natural contamination. So you see the scale of the research. Here's our Web of Science. It's the number of publications per year. This is a citation. So over 3,500 articles and over 100,000 citations occurred. The most cited paper is Janet's. It's still the most cited paper. You say arsenic groundwater or surface composition model. So that's the most cited research paper. Decades of research have produced our knowledge base on what are factors controlling arsenic concentration in groundwater, and what are the mechanisms that release arsenic to groundwater. And that knowledge base allows people to do machine learning predictions of arsenic concentration in the world, or in this case, the US. So this is a map from Joe and Michael's paper in Science 2020, shows the arsenic concentration distribution in the world. This is a paper about the predictions in the glacial aquifer system in the US by the US GS people. Now, policymakers and environmental managers, they love this kind of data. So like the state of Indiana, they say, well, tell me where arsenics are, right? So they only have limited budget. They want to focus their funds to troubled areas. Now, in some sectors of the hydrologic cycle, the physical methods are not very effective quantified fluxes. Now, isotopes and chemical traces provide volume and time integrated estimates. That's particularly true for the submarine groundwater discharge. So we know back probably like 1868 that submarine groundwater discharge into the coastal ocean must be important, but only in this century, people have used the isotraces to figure out about 1 to 10% of all the fresh water discharged into the ocean actually from groundwater. What's more important is that in the coastal ocean, the geochemical budget, the nutrients, the metals, the isotopes, this from a lot, very significant components from groundwater. Groundwater recharge are very important to groundwater flow models. You put in different recharge numbers, you get a very different results. This is a number very difficult to estimate, but this is particularly true in arid and semi-arid areas. Isotope tracers provide time and volume integrated, and that shows great promise. This is just the number of papers people published on the submarine groundwater discharge in this century. So in this century, we see that the geochemical kinetics knowledge has reached a critical level. We have accumulated a lot of laboratory studies of dissolution rates at far-from equilibrium on mineral powders. We have a lot of data on rate dependence on the temperature, pH, and other factors. Most of this data are in the compilation by the USGS report here. And here I also show there are many papers published on geochemical kinetics. We see significant advances in surface absorption studies. Now, many contaminants of lead, arsenic, they have concentration at a part per billion level. So they're not controlled by the solubility of the mineral that they are major constituents. They're controlled by surface absorption. And we in the subsurface has very large mineral surface area to volume ratios. So from the research, we know that the iron manganese oxyhydroxide commonly play a major role. Even they constitute only various tiny fraction of their bulk rocks, soils, or sediments. And because this oxyhydroxide are tied to the redox cycle, contaminant transport can also be tied to the redox cycle. Back. Geochemical modeling has transformed. Now it's almost ubiquitous tool, largely thanks to the USGS software FreakC, which is free, and it's very easy to use. Now, online web-based computing has a future. So my student put this FreakC and a few other computer geochem modeling tools online, so people can don't need to download and install their own computers. And since they started tracking that in June 2020, they see over 4,000 visitors and probably close to 1,000 repeated users from all over the world. And I'm particularly happy to see that people from South America and Africa and South Asia are also able to use the free open source web-based modeling. Now, this is also, geochem modeling is great to make this science results accessible. Some of our models, like a CO2 solubility model, a lot of people use our model. They are like 5-10 page equations, right? So they program into this calculator so the users just can type in the temperature, pressure, salinity, and they get this kind of data. So that's a very effective on web-based modeling tool as well. Okay, now let's have some fun to predict the future. As Mark Twain said, and prediction is always difficult, but particularly about the future. I think that going forward, climate change mitigation and energy transition are the major drivers. Now, many of you probably heard about the U.S. passed a new legislation, IRA, Inflation Reduction Act. So there's a $369 billion for climate change mitigation and energy transition. In the fall of last year, I made a Darcy tour on the East Coast. So I went from University of Pennsylvania, Princeton, Columbia, Dartmouth. There are a lot of energy, a lot of talks about that. So a lot of activities happening is that they don't want to only have the government support for those efforts, but also they want to have the support from private sectors, private foundations, private corporations, and a lot of money putting into those efforts. So I think that's the major driver. And water scarcity, water quality is always an issue. And going forward, by all indication, we're getting worse. So that will drive hydrogeochemical study as well. So let's take a look at the climate change mitigation. Okay, so most of you are very familiar with this kind of diagram, right? So this is a diagram. They say it's adapted from IPCC report. And this is the year, this is the gigatons of a CO2 emission or CO2 equivalent. Now, the gray areas are the avoided emissions. So by alternative energies or by CCUS. Now, the blue areas are remaining emissions and the green areas are negative emissions. So according to International Energy Agency, reaching net zero emission will be virtually impossible without CCUS and negative emission. I forgot to mention that the goal is less than 1.5 degrees, and to achieve this goal, you want to have net zero emission by 2050. But IEA says that reaching net zero emission will be impossible without CCUS and negative emission. So what are CCUS and negative emissions? CCUS stands for carbon capture, utilization, storage. So in this cartoon, you capture CO2 at a power plant, transport it into favorable geological location, and then inject it into deep aquifers for storage for a long time. So in that sense, CO2 is sequestered from atmosphere. A lot of people don't like this cartoon because it implies continued use of fossil fuels. So people favor negative emission technologies. But negative emission technology also need CO2 storage. For example, if we directly capture CO2 from atmosphere using this machine made in Switzerland, you still need to store the CO2, right? Another negative emission technology scheme is called BECCS, bioenergy with carbon capture and storage. Instead of burning fossil fuels, you burn weeds. By growing 500 million to 2 billion acres of weeds, you remove CO2 from the atmosphere, then you capture CO2, and that captured CO2 also need to be stored. So CCUS, CDR, or BECCS, they all need to capture CO2 to store in geological formations. So where's the connection with the hydrogeochemistry? Well, when you inject CO2 into aquifers, it causes a lot of geochemical reactions. So for example, this is the cartoon from my former student, Penlu. So this is a targeted geological formation, say a sandstone. Over top of that, you have shale or cap rock, prevent the CO2 migrating upwards. Now, the injected CO2 is supercritical CO2. So near the wellbore, there will be immiscible CO2 plume. Then CO2 is going to be dissolved into water and then acidify the brine. This is a very similar process as people making Coca-Cola in a movie filter. I see people do that. You have a barrel of water, you put a sugar powder in, and then you put a CO2 in. And the Coke is very acidic, like pH 2.6 or 2.8. It dissolves our teeth. And here, the pH is like a 3.5, 4.5, but it's the temperature is also higher. So you have hot, acidic, corrosive fluid that will dissolve the minerals already in the aquifer and precipitate the secondary minerals and cause change process permeability. Now, if the precipitated minerals are carbonate minerals, like calcite, anchorite, siderite, then we call this mineral trapping or CO2 mineralization. And now you see this chemical reactions, right? So here, the precipitation, we need to know the kinetics of this precipitation and the dissolution reactions. Now, sandstones are not very reactive, but if you want to store CO2 into reactive aquifers, like basalt aquifers, then the reaction dominate. So there are two pilot studies in the world on storing CO2 in basalt, one in the Washington State, the United States, and one in Iceland. I think Switzerland is involved with this storage in aquifer in basalt in Iceland. So those are pilot study, very small scale, and people find out like 75 to 95% of the CO2 injected turning into mineral calcite and anchorite in 2 years. So the reaction is very important. Like you don't have a cap rock to prevent the CO2 moving upwards. You rely on the reactions. But if the reaction too fast, then it's not good because it clogs the microfractures in basalt. Now here's a picture of the mine tailings. People also want to store CO2 in mine tailings. Like you rely on chemical reaction like this, say olivine reacted with a bicarbonate and precipitated out as carbonate mineral, right? So CO2 is mineralized. Those reactions also depend on kinetics. Now there are publications, peer-reviewed papers, they say no kinetics, just equilibrium. All these reactions instantaneous, but then you get a reduction number. So mine tailings can remove 1.5 to 4 gigatons of CO2 a year, and then after a couple of years, they corrected themselves. So actually, kinetics is very, very important, right? And then you need geochemical modeling, right? So, or storing CO2 in aquifer, soil, in the coastal oceans, you all need to predict the future events, right? It's in your site selection, your design, your permitting applications, and you predict this CO2 mineralization through geochemical modeling. Some of you probably know that my book with Greg Anderson on geochemical modeling. In the book, we lay out very clearly you need 3 pieces for all geochemical models. One, you need an input file, which is specify your conceptual design of the chemical system and also have the site-specific information. You need a computer code, then you need a thermodynamic kinetic database. This is where the basic science is, right? So we predict the future. We must understanding the reaction mechanism at the most fundamental levels. Now, this is where the basic science is connected to the applications, right? Now, for the applications, if there's mitigation, climate change mitigation going forward, you have thousands of projects around the world, and you need all the permitting process and monitoring process, right? But you need a basic science. You know the thermodynamic kinetics in order to make the reasonable predictions. This is also a peculiar situation that the basic science needs to catch up with the bold proposals. I think we know the thermodynamics well, except some very stubborn problems we cannot solve. We know the CO2 solubility well. The real knowledge gap is the kinetics, the rate constant and the rate law. So let me introduce a little bit about geochemical kinetics, so provide some background. The geochemical kinetics is the study of reaction rates and how rates are affected by factors like pH, temperature, ion concentration, catalysts, and inhibitors. You can define the rates as change in concentration per unit of time, or you can write a little more fancy equation, say the change of silicon concentration here per unit time, while you keep other factors constant. Let's look at an example to see what does that mean and how we measure them. Say let's measure the quartz dissolution rates, right? It's a relatively simple for chemical compositions. And so quartz is dissolved and the silica get into the aqueous solution. Now we first find a good crystal of quartz, or crush it and then put it into the reactors. And then at a predetermined time, we take the reactor down and measure the silicon concentrations. So we build a concentration versus time curve. And using that curve, we measure the reaction rates, right? So the geochemists have been using this method since at least the 1930s. So I call this the conventional method, right? You have concentration and you have time here. Now, if you look at this graph longer enough, you see a few problems. One is that the reaction is very slow. So these are days, so these are 1,000 days. No grad student like to do this kind of experiment, so you don't have data until a few years later. Also, you see that near equilibrium, the concentration increase is very small. So it's a rates very difficult to measure. Now, you have much longer time that it eventually will reach equilibrium, right? So at equilibrium, the concentration is constant. So you cannot use this method to measure the rates at chemical equilibrium. But let me see, going back. But near equilibrium is where the data we need. So let me define what is the near equilibrium rates, and I know it's highly technical. Let me use this diagram to explain this. So this is the Gibbs percentage of the reaction, and this is the net reaction rates. So at a chemical equilibrium, this percentage is 0. The net reaction rate is 0. The white area is far from equilibrium, and this shaded area is close to equilibrium. Now, as the system moves from far from equilibrium to near equilibrium, the thermodynamic drive for the reaction diminishes. So you see the rates decrease here. Now, we have about 1,000 measurements on silicates at far from equilibrium. Right? I mentioned about the USGS database. We only have less than 30 measurements in the near equilibrium region. Because this measurements are very difficult, reactions are very slow, and secondary phase likely precipitate, which complicate the interpretation. But if you look at the typical surface water, river water, lake water, groundwater, and soil water, they're all in this region, near equilibrium region. So we don't have the data where we really need it. So that's the state of knowledge here for reaction kinetics. We have a lot of data at far from equilibrium, measured on mineral powders in the laboratory. We only have a few experiments on near equilibrium. The quality is questionable. And a few experiments show that it does not follow this line really, except the quartz, because this is really the rate law that for the elementary reaction, not for bulk reaction. So we must have some kind of innovation to overcome the challenges and get into the near equilibrium region. Now, one innovation is to use isotope ratios rather than concentrations. That will give us orders of magnitude more sensitivity than the conventional method using concentrations. It also allows you to measure the rates when secondary phase precipitate. We can look at an example here. So this is the albite dissolution at ambient temperature, pH 5. This is dates. This is the concentrations. You can see the reaction is so slow. The concentration increase is small, and you cannot, using concentration, define dissolution rates. But if you use the isotope, like say the silicon-28 fraction, then you clearly define dissolution rates. Now, the isoprotrusive method is not really a new innovation, or certainly not my invention. The chemists who won Nobel Prize in 1940s, they really thought about that. And the biologists published books in the 1960s using isoprotrusives to study kinetics. And in the 1990s, some French geochemists, they tried this, and they did not get it very far. So what really helped is the advancement of the analytical technology. So this is a multiple collector ICP-MS, right? So that makes the measurement of a non-traditional stable isotope like silica much easier. So we know how to measure silicon isotopes back in 1950s, but at that time you probably get a better chance to get yourself killed than get some good results. But now this is much easier. So you really need to have 3 different pieces to use this method. You need to have instruments and analytical methods. You need to have the reactor experiments, and then you need a solid knowledge in kinetics and thermodynamics so you can interpret the data. So in the last 10 years, my students and collaborators, we have used this method. The method now is mature. It's ready to be deployed, and I think that will advance the field of geochemical kinetics. Now, this is also a good story about sabbatical leave. I learned to use non-traditional stable isotopes from my sabbatical at ETH in Alex Holliday's lab. It's Alex's generosity really helped the different branch of science advance. Let's see how that work. So let's look at L-byte. Keep saying L-byte because feldspaths make up more than 50% of Earth's cross volume. So L-byte here have 3 stable isotopes, silicon-28, 29, and 30. And here using those numbers are fractions. So we adding them together is 1, right? And in the laboratory, I prepared a solution that almost pure silicon-29, and then added the crushed L-byte into the reactor. So now I created a 2 n-member system. So all the silica in the solution, either from the initial solution or from the dissolution of L-byte. So by monitoring the temporal evolution of the 29 to 28 ratios, I get the L-byte dissolution rates. Now you probably think that a question that isotope will fractionate. It does, but because I use such a strong spike, the effect of fractionation is negligible. This method is also called isotope doping, spiking, labeling, and dilution. We can look at one experiment, say L-byte dissolution at ambient temperature pH 5. So here's the reaction dates, and this is a fraction of silicon-29 in water, and this is silicon-28 in water. And each symbol represents a reactor sacrifice for their silicon isotope analysis. And you can see that I prepared a solution almost pure silicon-29. And the L-byte mostly has silicon-28. So as more L-byte is dissolved, the silicon-29 in the solution decreases with time, and 28 increases with time. And using this mass balance equation, I can get the L-byte dissolution rates. In fact, I have 2 equations. I can solve 2 unknowns. I can also get the silica precipitation rates. So here you see this is the isoprotrusive method. This is the conventional method. That's the diagram I showed before. And you see we have orders of magnitude more sensitive analysis. The isoprotrusive method also gives us a new type of reaction rate, which is unidirectional rates. So I'm using L-byte as an example here again. So L-byte dissolved, and I use this, you see the arrow here is one directional, right? And the reverse reaction is the precipitation reaction. Now, in the past, the conventional method, people always deal with the net reaction. They don't have the unidirectional reaction. But the most useful part of the isoprotrusive method, and people know that for some time, is that if there's secondary phase precipitate, I still can measure the rates. And that allows me to study the near equivalent system. Because you can see that the L-byte dissolution Like if I spike with a very strong spike in the solution, it's very sensitive to about how much L is dissolved, but the precipitation does not change the isotope ratio very much. Now, this is the concept very difficult to explain. It took me a while, but in this picture, I'm holding a bowl of asparagus soup, right? Eating the soup, getting the less soup in the bowl, but does not change the pepper to other ingredients ratios. Similarly, in the reactor, if we have a silicon containing phase precipitating, it will reduce the silicon concentrations, but does not change the silicon 29 to 28 ratio significantly. Significantly because there's fractionation going on, but if you use very strong spike, the effects is negligible. So with this feature, now I can deal with the near equilibrium system. All right, so let's do some experiments, ask some fundamental questions. Say, what does it mean L by dissolution reaction is irreversible? And how should we actually modeling this kind of reactions? So we did experiments at 50 degree and a pH of 6.3, which is very near neutral pH. And so these are reaction dates. Here I plotted the saturation index of the system. So at equilibrium, the saturation index is 0. Now, after 7 days, the system moved from far from equilibrium to near equilibrium. And in the near equilibrium system, the silicon concentration variation is very small. But we still can use the isotope ratios, the fraction of silicon 28 to clearly define dissolution rate. So we were able to measure unit reaction rates in very close to equilibrium. Now, if you look at the system, solution chemistry, in this near equilibrium system, many secondary phase are supersaturated. So you see here is kaolinite, olefin, immogolite. And so that's people always suspect. We have this 20 or 30 near equilibrium experiments in the literature, whether there are some precipitations. And we did see some precipitation on the L surface. So in other words, it's difficult or impossible to prepare a solution that is very close to equilibrium with the feldspaths, but it's not a supersaturated solution. So now we found a way. We can, using isotope matrices, we can deal with this system. Okay, so now we can decouple the dissolution and precipitation reactions. We see the dissolution continue to occur. The precipitation, the reverse reaction is negligible. Instead, we see the precipitation of amorphous phases like olefin and immogolite, and these two reactions are coupled, and there's a coupling of these two reactions keep the system very close to equilibrium, but not equilibrium, and that's how the system keep functioning. So that makes sense. At the 50 degree, the energetics still favors polycrystalline amorphous materials, not the crystalline L by precipitation. And so our results clearly show that L by dissolution, this condition is irreversible. But this is nothing new, right? So you open up every geochemistry textbook, they tell you feldspar weathering is irreversible. But here we dig a little further. What does really mean reaction is irreversible? Like we decouple the reaction and how we should model it. Now, we know that feldspar weathering is an irreversible reaction, but using this rate law, unwittingly model feldspar weathering as a reversible reaction in the literature. Now, almost all the geochemical modeling studies, any studies including geochemical modeling, use this rate law. And this is derived from the principal detail balance, commonly called the transition state rate law. So this is a forward reaction, this is a reverse reaction, this is a net reaction from these lines are from this rate law. And if we see our experimental system is here, so if we use this rate law, we are modeling the reverse reaction. If you look at the field data, so this is soil water, groundwater from the granite reservoirs in Georgia, you see that fall into the near equilibrium region. If you use this rate law, then you're modeling the reverse reaction. This is equivalent to say that part of this rust chain turning back to shiny metal, or soils on the granite outcrop turning back to granite. which is, it's not right. So instead, I'm trying to say that we see at the low temperature system, we see the unidirectional dissolution reaction only. And this is coupled with the precipitation of kaolinite or other clay minerals. And that's what irreversible reaction mean, and how should we model irreversible reactions in the future, how in aquifers that store CO2, in the soil that store CO2. Now we have a method that is can measure unidirectional rates, more fundamental properties. We can measure rates at a condition unattainable before, like near equilibrium, at equilibrium, and near neutral pH and ambient temperatures. Now we can use this method to address many knowledge gaps in geochemokinetics for climate change mitigation. I choose to study silica isotope only first because, as you know, that the Earth's crust is made up of 90% of silicates, so we can have many important research topics. In 2020, I organized a workshop to introduce this method. About 300 participants came and from 34 different countries. The recordings of the lectures are available on this website. I also found that some productive labs, geochemical labs in France and in Canada following this method. Now this method is general. We can use other non-traditional stable isotopes like barium, calcium, magnesium, iron, and study the kinetics of carbonates, sulfates, sulfide, and oxides. I have used the barium isotope to study barite dissolution or precipitation at the chemical equilibrium. This is very important for paleoclimate studies. As you know, that the paleoclimate proxies are using the trace elements, the isotopes in minerals, the carbonates, the sulfates, right? And so you go back to a few thousand years, back to many million years. The big assumption here is that once barite or other minerals precipitated, they're at a chemical equilibrium. You have reaction very fast. That's the assumption, nothing wrong. Chemical equilibrium. And therefore, they stop reacting with the water, and therefore the information that preserved is like time capsule. So now you can open up and to get to the paleoclimate conditions, so like the temperature, paleosalinity, pH, ocean productivity. That contradicts with the basic principle we learned in high school. Probably I forgot it myself as well. That at a chemical equilibrium, reaction do not stop. Just the forward and backward reaction rates are equal. So, but people did not have a way to measure the reaction rate at a chemical equilibrium either. As I mentioned earlier, that at a chemical equilibrium, the concentration constant. So you cannot using the concentration with the time curve to get to your the reaction rate at a chemical equilibrium. And my students searched the literature, and they only found 3 papers that shows chemical reaction rates at a chemical equilibrium. So now we have isotopy method. We have measured the rates for barite. We have measured the rates for quartz at a chemical equilibrium. And so now we have a method to test the fidelity of this paleoclimate proxies. It's a very sensitive topic. So this is a little sidetrack, but let's come back to climate change mitigation. Now this is a map of current completed and planned CCUS project around the world. We need thousands of this kind of projects and to store hundreds of gigatons of CO2 in aquifers. Now this is a lot of CO2 to store in a lot of aquifers. In the pandemic, I attended some seminars in the UK, and they discussed what are kind of a potential impact on earth sciences if those kind of program is partially implemented. So I repeat some here. It will create a new industry at a scale equivalent to the oil and gas industry. It would train a new generation of earth scientists, and it would demand a new level of understanding of surface hydrogeology, another golden age for hydrogeology. Another big trend, I think, driving a lot of things is energy transition from fossil fuels to clean or renewable energy. The electric cars need about 70 times more metals than the internal combustion cars. So the energy transition need a lot of critical minerals. So this is map, is a graph from International Energy Agency, and they show that we need 7 times more rare earth elements and 42 times more lithium in 2040 relative to 2020 for this energy transition. I just got a very large grant from Department of Energy with a large group of people to study rare earth elements, and also have a collaboration project to explore the potential environmental product consequences of mining lithium in Czech Republic and in Germany. Now, this is a map from this paper published in Nature Communications. They show that if you want to meet this demand of critical minerals, you need to disturb about 50 million square kilometers of the earth. Now, past mining activities caused all those things we know. And so for the energy transition, we really need to protect water resource. We also need to protect the people in developing countries. Many critical minerals are mined in poor countries. Water resources crisis is already here. And here you probably also see a lot of fresh mineral surface, which are ready to react with CO2 water and cause this kind of damage. And so you need geochemical kinetics and you need a geochemical modeling. I think water scarcity will continue to drive hydrogeochemical studies. Because early this month, we have a video from John Cherry, and he gave us a talk. He warned us that the societal single vision focus on CO2 emission reduction, right? I want to remind the people that the water is so critical for a sustainable world. I agree. Now, some of the emerging or increased water resource management practices like managed aquifer recharge, river bank infiltration, there are a lot of hydrogeochemical reaction going on that we need to study. We also need to concern about emerging contaminants. And then there's a nexus of the water, energy, climate, right? So you want to deploy the schemes of bags of critical minerals and have rock weathering that can also greatly influence water quantity and water quality. Okay, so I think I gave you a very loaded talk in like 45, 50 minutes. I hope you who are not in this field, I hope you have a better idea what is hydrogeochemistry. It studies water quantity and water quality. It's a very small branch compared with physical hydrogeology, and it can play a much bigger role if we have a better integrated with the physical hydrogeology. Now, in the 20 years in the first part of this century, we see large amount of research on arsenic contamination, the successful use of isotope tracers for submarine groundwater discharge and aquifer recharge. We see advances in geochemical kinetics and surface absorption studies and geochemical modeling. I'd like to draw your attention to the scale of the climate change mitigation and energy transition efforts and the potential impact in our field, and really call out for the need for basic research to support them. We have very bold proposals on the table. We need basic research to support them. Finally, I'd like to call on hydrogeochemists to be willing to work on what the societal needs and make research results accessible. After all, this is the spirit of Henry Darcy. Thank you very much.
Thank you very much, Chen.
Yeah.
So now we have time for questions.